We're surrounded by data models. They're predicting everything from what movie you'll like to whether a bank transaction is fraudulent. But here's the thing. What if the very data we're feeding them is flawed from the start? There are these hidden traps just lurking under the surface that can make our models get things completely wrong. So let's dive in and uncover them.
So picture this. You've got your data, you've picked your algorithm, and you are ready to find some amazing, groundbreaking insights. But what if there's something hiding in that data that's going to totally sabotage your work before you even begin?
That's why today we're going to run what I like to call the data scientist's gauntlet. I'm going to be your guide through 3 of the most common, most treacherous traps in data science. The goal? To help you spot them, fix them, and build models that aren't just accurate on paper, but that we can actually trust.
All right, first up on our gauntlet, a little something called multicollinearity. The easiest way to think about it is like a confusing echo in your data set. It's where your different features start repeating each other, making it almost impossible to hear the true signal you're looking for.
See, in a perfect world, we want our predictor variables to be connected to the final outcome, but we really don't want them to be connected to each other. When they are, it's like having identical twin basketball players on the same team. A point gets scored, but who do you give the credit to? The model gets just as confused. It just can't figure out which variable is actually doing the heavy lifting.
Okay, let's make this super concrete. Imagine you include both a person's weight in pounds and their weight in kilograms in your model. That's perfectly redundant. It's the exact same piece of information, just said a different way. A slightly less obvious example? Including both BMI, that's body mass index, and weight. Well, because think about it, BMI is literally calculated using a person's weight. So the two are super correlated, and throwing both in just creates noise. And this leads to a classic, super common mistake called the dummy variable trap. When you take a category like gender and you turn it into numbers for your model, it's really easy to create perfect multicollinearity. Just look here. The is male column perfectly predicts the is female column, right? If one is a 1, the other is always a 0. The fix? Oh, it's so easy. You just drop one of the columns. The model already has all the information it needs from the one that's left.
Okay, so how do we catch these data echoes like the pros do? We use a special metric called the variance inflation factor, or VIF. Seriously, calculating VIFs is the absolute gold standard for diagnosing this problem. Basically, it gives each variable a score that tells you how much it's already being explained by all the other variables in your model. And the process is pretty straightforward, actually. First, you calculate a VIF for every single one of your features. Now, a common rule of thumb is that any score over 5 is a big red flag. So you find the variable with the highest score, you take it out of the model, and then, and this is the crucial part, you recalculate the VIFs for everything that's left. You just keep repeating that process until all your scores are down in a healthy range.
All right, so we've silenced the echoes. Our variables are all distinct. But now we face a different kind of problem. What if the data itself is just fundamentally lopsided? This brings us to trap number 2, the problem of class imbalance, or what I like to call the underdog problem. And this one is especially critical in really high-stakes areas like medicine or finance.
Just take a look at this. It's a data set for credit card transactions. A whopping 98% of them are totally legitimate. Only a tiny 2% are actually fraud. This huge skew is exactly what we mean by class imbalance. And that tiny little 2%? That's our underdog. And you know what? It's the only thing we actually care about finding. Okay, so here's a question for you. You build a model, you run it on this data, and it comes back 98% accurate. That sounds amazing, right? A+ work. But what if I told you that model could be a complete and total failure? How on earth is that possible? Well, here's the dirty little secret. A lazy model can score 98% accuracy by just guessing the most common thing over and over, in this case, not fraud. It looks fantastic on paper, but it has completely failed at the one job it had, to actually catch the fraud. That 98% accuracy score, it's not just useless, it's dangerously misleading. So, how do we fix this? How do we give that underdog class a fighting chance? Well, data scientists use a few cool balancing techniques. We can do what's called oversampling, where we just make more copies of the rare fraud cases. Or we can do undersampling, where we delete some of the normal, non-fraud cases. Or we can get even fancier and use smart algorithms like SMOT to generate brand new artificial fraud examples that look real. Okay, our data is clean, it's balanced, we're feeling good, right? But hold on, there's one last, kind of weird challenge, and that brings us to the final stop on our gauntlet, the curse of dimensionality.
This is what happens when your data has way too many features, and it's like your analysis turns into this giant, confusing maze. You know, we're all taught more data is always better. And when we're talking about more rows, more examples, that's usually true. But more features, more columns, that is a totally different story. Piling on too many predictors can actually, and this is wild, make your model way, way worse.
Let me give you a rule of thumb to wrap your head around this. For every single feature or predictor you add to your model, you should have at least 10 subjects or rows of data. So if you have 100 features, you better have at least 1,000 data points to support them. If you don't, you're starting to wander deep into that maze.
So what is this so-called curse? Well, as you add more and more dimensions, or features, your data points get spread further and further apart from each other. The data becomes sparse. It's like trying to find your friend in a small room versus trying to find them somewhere inside a 100-story skyscraper. It's just so much harder to find patterns, and your model is more likely to just memorize random noise instead of learning the real signal. We call that overfitting.
So, how do we get a map for this maze? Well, the main tool we use is called Principal Component Analysis, or PCA. It's this really clever technique that reduces all that complexity. PCA intelligently mushes together your many features into just a few new, powerful principal components that hold most of the important information. It basically gives you a simplified map to navigate the maze.
And just like that, we have made it through the gauntlet. By learning to spot these 3 traps, we can stop building fragile models that look good but are secretly wrong, and start building ones that are strong, reliable, and actually useful.
So let's quickly recap your new toolkit. For the data echo of multicollinearity, you're going to check your VIFs to find and remove those redundant features. To help the underdog in a dataset with class imbalance, you'll use balancing techniques like oversampling. And to escape the data maze of high dimensionality, you'll use PCA to simplify things. And I want to leave you with this one last thought. Now that you know what to look for, the echo, the underdog, and the maze, how does this change the way you look at all the AI-driven headlines, the medical studies, and the business reports you see every single day? What hidden flaws can you see now?